I'm going to be talking about ZULF-NMR, and what motivates me personally about ZULF-NMR a lot is the potential to miniaturize NMR and to potentially drive it towards applications that are portable NMR, and maybe as a dream, as a goal, to be able to do this on your cell phone. And I do think that especially Michael Taylor, who's talking right after me, is particularly close to this goal. So that's, of course, very exciting. And so we shall see how this research unfolds. But of course, exactly as Kirill pointed out, this talk is sort of about covering some basics, and I will be explaining various aspects of the basics. And I guess the other thing that I really want to point out, if you do have any questions, I'm certainly happy to spontaneously take questions in between. As far as I'm concerned, you can just unmute yourself and ask your question at any time. So I want to thank my lab that I've now been running at NC State for 2 years, and it's been an exciting time. And certainly we're also now starting to also go back into the ZULF regime and starting to do some research in that direction. And so I'm going to share also with you some kind of small little insights that we've been able to do so far in our lab now. But also, of course, all of this work and everything would have never been possible without the help of all the collaborators over the years. And because this goes back especially to my PhD time, I do want to very much thank Alex Pines and Dima Bodgar to help me along so tremendously in my career, and Warren, my postdoctoral advisor, of course. And then there's one more person on here that I really want to give a shout out to, which is Micah Ledbetter, who, in my mind, really is one of the central figures that has established the ZULF field, and he taught me all about ZULF, and also has published one of the sort of most important initial papers. So nowadays, NMR is done oftentimes in very large, expensive magnets, and it's very difficult to create such strong magnetic fields because you need superconducting wire and a very strong current. And the question is, how can we transfer this technology to cell phones and get rid of the superconducting NMR and make it into a portable device that can maybe be integrated with microfluidics, and then eventually, you can hopefully carry it in your pocket. And of course, there's a good reason why we all work at very, very high magnetic fields with normal NMR, and that is because the signal actually increases with the frequency squared, or the magnetic field squared. And so I think it's worthwhile to really examine why that is and to see what we can do about it. So the first factor that makes the signal stronger at higher magnetic fields is from thermal polarization, just by the mere fact that if you take a sample and you stick it into a magnet, then you get more polarization that you can harness to get a signal. And here, it's quite obvious that what we can do, since we all love hyperpolarization technologies, we can use a hyperpolarization technology that does not depend on the magnetic field, and therefore create your polarization at any magnetic field. And then there's the second factor of omega, which has to do with the fact that we're using inductive detection. And inductive detection depends on the derivative of the movement of the current, and therefore it becomes more and more sensitive as the frequency gets larger. But this is not necessarily true for other magnetometers that have been emerging over the last decades, and maybe even more recently. And typical examples that you may be aware of are rubidium magnetometers, cesium magnetometers, NV diamond for detections. You can use squid magnetometers, and other techniques such as Faraday rotation, for example, that are also proving to be extremely sensitive. There's also GMRs, giant magnetic resistive detectors, for example. Now, there is unfortunately yet another reason why it makes a lot of sense to go to high magnetic field, which is that you get much more chemical shift dispersion at higher magnetic fields, which means that there is a lot more information you can get out of the NMR spectrum, simply because you're spreading out the peaks, and then you can resolve them better and really kind of read all the information. I do think that this is a challenge for ZULF-NMR, but one good thing is that we can actually get very, very narrow lines at low magnetic fields, because it's oftentimes very easy to shim low magnetic fields. And also the J-coupling does not scale with the magnetic field. So the chemical shift, if you go to a higher magnetic field, you will always get more and more separation between the lines. Whereas the J-coupling does not depend on the magnetic field. And therefore, even if you are at a low magnetic field, you can still use the J-coupling to differentiate, to split out the lines and still learn all the chemical information that you want to learn from your systems. And so then, if all of this can be done, then we're moving from a very complex and expensive sort of NMR modality that really has been driven sort of by going to higher and higher magnetic fields, to a system that hopefully doesn't require any cryogens, is small, can fit in your pocket, and has easy shimming associated because there's no magnetic field, for example, if you go all the way down to zero magnetic field. And so the overall vision is that we're replacing sort of the NMR magnets that are in the background and are fading away with new devices that we're developing in the ZULF world. So that's by way of introduction. And so now let me give you an outline for the rest of the talk. So first, in part A, I'm going to basically just explain the basics of experimental procedures, how to do NMR detection with atomic magnetometers, and specifically how it was set up at Berkeley when we first did these experiments. Then I'm going to spend part B, after sort of a question and answer session, on introductory spin physics to ZULF-NMR. So what are sort of the main concepts that you should learn and be aware of in order to really be able to treat ZULF-NMR well and understand the spin physics of it. Then again, after a short question and answer session, I'm going to use those concepts and apply them in sort of some kind of advanced topics. And this is what happens if the spin systems get more complex, with many J-couplings, and maybe there's a perturbing field around. Then I want to talk about a very subtle thing that I think is going to be quite interesting moving forward, which is that if you detect your signal out of various directions in the presence of a perturbing field, so let's say your direction of detection is along the applied magnetic field or 90 degrees to the applied magnetic field, then the spectra that you observe at very low magnetic fields change in very interesting ways, and it's certainly worth a second look. And this is something we've recently been doing, and I want to explain some of that. Then in part 3 of the advanced topics, we're going to talk about parahydrogen effects and how we can use parahydrogen to enhance zero field NMR. And then in the last part of my talk, I wanted to take advantage of today's opportunity to also talk a little bit about some of about 2 papers that just came out or are in the process of being accepted, and that is the PHIP Razor and NV-detected Saber. So actually, I'm going to just, as a teaser, start with part D to give you like a brief overview of these 2 things that are currently being published. So the first
Thomas, can I quickly just interrupt you, because there is a question, and I'm sure you will cover that, but still it's good to.
Yes.
Yeah. So what contributes to easier shimming at low fields? is it smaller size of the measuring volume or less susceptibility difference or other factors?
So I think it kind of depends on the range. The way I mean it in this moment, and the very easy answer, is that if you have no magnetic field because you're at zero field, then also it's very easy to shim. So obviously all you need to do is try to make your field as close to zero as possible, and then you will be able to get very narrow lines. If you move to like higher magnetic fields into the millitesla regime, this argument of course becomes much more difficult. Shimming is not as easy as I make it out to be maybe here at first sight, but it is certainly true that susceptibility artifacts are reduced.
Yeah, thank you.
Yeah. Okay, good. So yeah, I want to basically, at the end of the talk, end of the session, show you how it is possible to detect 1 millimolar solutes in volumes that are on the order of picoliters. And I think this can be very exciting in the context of looking at sort of biochemistry on the surfaces of NV diamond chips, for example. The other thing that I want to mention, so I guess it is because we're in the ZULF talk, it is worthwhile to say that these NV detected experiments were done at 6.5 millitesla, and that's because Saber is very effective at 6.5 millitesla. The other thing that is sort of emerging as an interesting topic that I think is very much worthwhile our attention are the PHIP razors. And that's, of course, primarily established by Stefan Appelt using Saber to do razor. And so we've been now engaged in a collaboration, and we've now have done this with various PHIP systems, also with hydrogenative PHIP, for example. And we're discovering all kinds of interesting effects where you have chaotic behavior, for example, at the beginning of your FID when your polarization is extremely high. And then you have things like, funny things like intermittence effects where first, one of the spins in your spectrum will actually be observable, HB, and then it switches back to HA, back to HB, back to HA, back to HB. And look at this FID. It lasts for 25 seconds. And so these are really kind of very fascinating effects that I'm going to be detailing. And I think what is kind of crazy is that it's actually possible to understand them if you spend enough time thinking about these effects. All right, so but back to the basics. So let's start with part A, which is about how do we what are the essential elements of a typical ZULF-NMR experiment, or NMR without the magnet, as it was sometimes called in the popular press. So first of all, if you want to do a ZULF experiment, it would be reasonable to shield the Earth's magnetic field so that you can get down to into the magnetic field ranges where the NMR frequency is 0. And when 0 is that, I mean, that you cannot really distinguish anymore between, say, protons, carbons, nitrogens with different gyromagnetic ratio, and they all have the same frequency and less than maybe 0.1 hertz of proton frequency or below. And so one way of establishing such a low magnetic field is that you take several layers of mu metal. Each layer of mu metal will provide about a factor of 10 to 100 in shielding, so that by the time you have put 5 layers around, you are in this regime that you want to be in, where there's absolutely no more magnetic field as far as the spins are concerned. Then in the inside of those shields, we set up an NMR tube, which is in green in the middle of the slide. And this is where we generate polarization in the spin system. And from this spin system, from the sample, some NMR signal, of course, has to emerge. So we have to kind of excite some coherences, and some magnetic fields have to emanate from this sample that then get picked up, for example, with a rubidium vapor magnetometer that is in the bottom of the green NMR tube. So in the bottom of the green NMR tube, you see a rubidium vapor cell. It's a glass cell filled with rubidium vapor that we heat a little bit so that the density of the rubidium vapor is big enough. And then this NMR sensor is operated with lasers, specifically in a pump probe setup, where we have a pump beam, which is on the right now, the red beam that is circularly polarized, and a probe beam in yellow that is linearly polarized in order to measure the signal that comes from the NMR tube. So just to like summarize just one more time again, there's some small magnetic fields that comes from the NMR tube, and these and this NMR tube sits on top of the sensor, and in the sensor there's a mechanism now that can actually measure these magnetic fields. So let's think about the details of this measurement of how these rubidium spins can actually measure a magnetic field. And so to understand this, first consider that the pump beam makes all the spins, all the rubidium vapor spins, the electron spins of the rubidium, to be aligned with the direction of propagation of the pump beam. So all the spins are pointing along the direction of the pump beam. Now, if this is the case, and the probe beam is linearly polarized and goes through this vapor, then actually it will not rotate. It will just go straight through because there is no component in the direction of propagation of the probe beam. But now, because of the action of a magnetic field that comes from the top, the spins, the electron spins, they start precessing around that magnetic field to some extent. At the same time, the pump beam pumps them back to where they came from. So some kind of equilibrium angle gets established that can now be read out by the probe beam. And we're going to talk about that in a moment, one more time. But I hope that I have illustrated sort of the overall components that are required for a successful ZULF experiment. So let's look at the guts of such a ZULF-NMR spectrometer in a little bit more detail. So oftentimes on the outside, the innermost layer of the shielding is a ferrite magnetic shield. And the advantage of that over mu metal is that there's less noise associated with a ferrite magnetic shield. And on this picture, you can see that you can kind of barely see the bottom of the NMR tube that sits right on top of the rubidium vapor cell. So the rubidium vapor cell is tiny. It's only just a few millimeters by a few millimeters in size. And then also you have the pulse coils. Those are used to manipulate the spins in the NMR tube and to excite coherences. In addition, it is important for us to do a little bit of shimming, and what I mean by that really is just adjust the magnetic field down with an X and a Y and a Z coil so that the magnetic field at the NMR tube is truly zero. And this is why we have these field coils that are a little bit larger put into the white plastic around close to the shields. Then you also see what is labeled a shuttling tube, and this is if you want to pre-polarize your sample, you need to shuttle your sample up and down. So oftentimes something typical that is done is that the NMR tube is shuttled out of this zero field NMR environment to pre-polarize it and then shuttle back down close to this rubidium vapor cell to do the detection. So that's an introduction to the individual parts and the picture of what it looked like. And so now we can talk a little bit more about the parts that are going on the outside to make this all work. So just a moment, focus on what is labeled polarizing permanent magnet. That's what we were talking about just a moment ago. And the NMR tube, which has the liquid shown in blue. And so if we are able to shuttle this NMR tube up and down, then we can, for example, pull it up, prepolarize it in the permanent magnet, and then shuttle it back down to the rubidium vapor cell in the middle, where then the NMR, the signal can be detected. The other important thing that I want you to mainly focus on this slide is actually the Wollaston prism and how that is used to actually measure the rotation of the probe beam. So you see the probe laser. The probe laser goes through the rubidium vapor cell, and what we're aiming to do is to measure its rotation. If the probe laser is perfectly linearly polarized, and let's say the rubidium vapor cell for now makes no change to this polarization, and it just continues straight through and hits the Wollaston prism, then the Wollaston prism is something kind of magical in that it splits up the light into equal components of left circularly polarized light and right circularly polarized light.
Thomas, can I just quickly ask the question which is connected to this slide? So just Quentin, I didn't catch the difference between the pump laser and the probe laser.
Yes. Yeah, so yeah, that's great. A great question. So the pump laser is typically higher intensity and is also directly on resonance with in terms of its frequency with the electrons, and it pumps all, and it's circularly polarized. What that does is it aligns all the electrons with the direction of propagation of the pump laser. The probe laser, on the other hand, is slightly off resonance, and the reason for that is so that it doesn't cause any pumping, but it really only does probing. And also, oftentimes, it could be lower intensity. And the other big difference between the pump laser and the probe laser is that the pump laser is linearly polarized, whereas the pump laser is circularly polarized, whereas the probe laser has linear polarization. Yeah. So, and linear polarization can be represented as equal amounts of left and right circularly polarization. So that means if you have perfect linear polarization and the probe laser goes through here, then in this Wollaston prism, you will get equal amounts of intensity onto photodiode 1 as you get onto photodiode 2. However, if there is now a small magnetic field present, which rotates the spins in the rubidium vapor cell just a little bit, so you're actually generating some component of polarization, of electronic polarization in the direction of propagation of the probe laser, then this probe laser will actually start rotating. And if the probe laser is rotated a little bit, what that means is that you basically change the intensity of the left and right circularly rotating components of this light, which means that the intensities on photodiode 1 and photodiode 2 are not the same anymore. And if you now measure a voltage difference of photodiode 1 and photodiode 2, you basically immediately learn about the magnetic field that is present inside of these shields that comes from your NMR tube. So just to sum it up one more time, the NMR tube produces magnetic fields. They influence the rubidium vapor spins. Depending on the action of the magnetic field on the spins, the probe laser will be rotated, and the rotation of the probe laser gets read out by detecting a voltage difference between two photodiodes after a Wollaston prism. So I'm going to explain exactly that same concept just one more time, okay?
Actually, there is several questions.
Yeah.
There are several questions, and I think, okay, so there is a question: is there is the sample shielded from the permanent magnet once it is polarized during the measure?
Yes. So the polarizing magnet is outside of all the shields. So once the sample arrives in the zero field region, no longer is influenced by that magnetic field, but it is polarized, and that polarization lasts on the order of T1, which is on the order of a few seconds. So we have to shuttle the sample down within a few seconds, ideally faster, maybe just hundreds of milliseconds, and then we can do the detection of the NMR.
Great. So the second question, do people use any other vapor cells, e.g. not rubidium vapor cells?
Yes, another typical vapor cell is cesium that also works quite well. An advantage of cesium, I think, is that you can operate it at slightly lower temperatures. So this disadvantage of rubidium is that we have to heat it. So in this particular configuration, we used to heat these rubidium vapor cells to almost 180 degrees, which is of course very hot, and so we needed good thermal insulation. But I think so one advantage of cesium, for example, is that you can operate it at lower temperatures.
And now there is one more question. What is the difference between a Wollaston prism and a polarizing beam splitter?
Oh, now you're asking me a question that somebody else has to answer. Do you know the answer?
Me personally, not.
It's a different geometry. It's still basically linear polarization.
Thank you, John. Okay, so actually then I can see one more question. How small do you think such an experiment can get?
So I think the biggest challenge with this type of setup is the shielding, really, of the magnetic fields, right? That you need these big shields to shield it. But otherwise, it can be tiny. So I guess what I'm arguing for, and I think this is something I want to pursue in my lab in the future, is that it probably does make sense to operate with some amount of magnetic field, maybe in the millitesla or so range. Because everything else can be really truly tiny and can totally fit on a handheld device. But how to accomplish the shielding of the magnetic fields in a very tiny handheld device, I think, is a little bit more challenging. And I'm definitely very happy to discuss all kinds of variants and options here.
Super. Yeah, I think, yeah, probably it seems that, yeah, at the moment, I can't see any further questions, so please.
Okay, so I've said it now already 3 times, but I know that this is kind of a difficult concept with how this detection of the magnetic shield works. So I do have it on yet one more slide. So bear with me just one more time. So imagine this. This is the BY field. So you have X, Z up, and Y is out of the paper, okay? And we have the probe beam propagating along X, the pump beam propagating along Z, and then the Y field is what we're trying to detect. So our magnetic field, let's say, comes from the Y direction. So how does this thing detect this magnetic field? So first of all, let's pretend there is no magnetic field. So the Y component is irrelevant, and we can only focus on X, what happens in X and in Z, okay? So first, the pump beam pumps all the spins into the direction of Z. So imagine this black arrow that is right now tilted to the side to initially be tilted only along Z because of the action of the pump beam, which is circularly polarized. Then, if that is the case, that means that this polarization has no component along X. Theta is 0 in the beginning when there's no magnetic field. What that does is that the probe that is linearly polarized will just propagate straight through the rubidium cell without being rotated. But now let's turn on a small Y field, a small magnetic field in the Y direction, which is in the or out of the paper plane, or your screen plane rather. If you do that, then this magnetic field will act on the spins that are along Z, and will start rotating them by some angle theta. And the reason why it doesn't keep going and just goes, you know, like your typical imagination is you turn on the magnetic field along Y, and then the spins will just start precessing in a circle around and around and around. But it does not happen that way. Here, instead, what happens is that some kind of equilibrium angle, theta, gets established at a given magnetic field. And the reason for that is because the pump is still on. The pump is on all the time. So you have two competing things going on. You have the magnetic field and you have the pump. The magnetic field drives the spins away from Z, and the pump beam pushes it back. So if you have an equilibrium situation between the pump beam and the acting of the magnetic field, this angle theta is established. And so what we need to do with the X probe is we need to basically measure this angle theta. And that's how the magnetometer operates. This is what gets read out. If you go through the details exactly, then you can derive the equation for the signal, which is of Lorentzian shape. You can see, if you go through the details, that as painted here, this thing is strongly dependent on By. So you have delta B, which is the width of this Lorentzian, times By, and that's what we're primarily trying to sense. But you can also see that there actually is also some sensitivity here to the X and the Z components of the magnetic field. So if we now take this signal and measure it and then also plot it, so here in the bottom you see a plot of the optical rotation, essentially of this theta angle, as a function of magnetic field, in this case in milligauss. And the interesting part for us in this plot is the center around 0. So what we want is we want a very, very strong slope and little noise. So in the area where the slope is very large, right around 0, that's where our magnetometer is going to be the most sensitive, and where we'll also have sort of the most linear relationship between magnetic field and optical rotation that we measure.
Actually, there is one funny question from Ricardo. Why is 90 degrees between pump and probe is the optimal angle? What do you think?
It certainly makes a lot of sense. Let me think about a logical answer here. I think okay. You know, I hope that the way that I have described the mechanism of operation makes it very logical as to why having a 90-degree angle makes a lot of sense here. With that, you know, just by the mechanistics of it, right, that you want to pump into the Z direction and then you measure the component into X by having a 90-degree angle. I feel like that makes a lot of sense. Yeah. In general, right, there are certainly ways of implementing these measurements that only use one beam. For example, you could have the pump, you could modulate it in interesting ways so that you use the pump for pumping as well as for reading. Those types of implementations sometimes can also work well. And that in terms of miniaturization, that could certainly be helpful. But maybe there's some sacrifice that has to be done in terms of sensitivity.
Thomas, actually, one more relevant, I think, question. Which parameter determines the range of linearity of the method? Is there something that can be tuned?
Yes. Which is the line width of this thing? So delta B. You can, for example, change the mixture of gases inside of your rubidium vapor cell. You can increase or decrease the density of the rubidium vapor, and all of those things, and you can change the temperature of your rubidium cell. All of those things will influence the line width of this Lorentzian that is detected. And by changing the line width of your Lorentzian, you will also change the slope here in the middle. And so one has to be a little bit careful, actually, because there's kind of an optimal for ZULF-NMR specifically. So for highest sensitivity to the lowest magnetic fields, of course, what you want is a very, very narrow Lorentzian so that you have the maximum possible slope. The big problem with that is that if you now want to measure frequencies that are outside of that range and maybe magnetic fields that get too large, then things break down. And therefore, it is kind of important to have a balance here where you set up your system in a way that your delta B is optimal for doing ZULF-NMR measurements, measuring magnetic fields in the right range, and also being able to detect all the different frequency components that you do want to detect.
Yeah, thank you.
Okay, I do want to come up with one equation. Of course, with Dima having established equation number 1, I need to also show equation number 1, which is the sensitivity of a magnetometer. And Dima's equation number 1 is the basically minimum detectable magnetic field for a given measuring time. And just look at this equation real quick so that you can identify its various components. So it's the gyromagnetic ratio of the electron, the number of atoms, the T2 relaxation time of the electrons, and then your measurement time, T. Now, this here is from a theoretical point of view, exactly the right thing to be thinking about. But since I'm trying to kind of teach you about sort of the experimental approaches and the basics of that, it might be also interesting to look at equation number 2, which is once you have put your system together and you've built it, and now you want to know what is the sensitivity of the thing that you built. How do you determine that, right? So in equation 2, let's say you apply a magnetic field, By, that you know, that you've calibrated, you've built the coils, you know what kind of magnetic field they produce, and you apply that magnetic field for a time t, and you measure your signal, maybe at a certain frequency, then you can maybe take the Fourier transform of your measured signal, calculate the signal to noise that you have, and thereby establish the sensitivity of your device. And I guess what is kind of important about this equation, right, is that it's independent of t. At first you look at it and it doesn't really look independent of t because you have the square root of t in there. But consider this, right? Your also increases with the square root of time because you do more averaging, right? And so in this equation, it would be expected that your answer that you get for your sensitivity of your magnetometer does not depend on the square root of time. And the answer for this equation will be in units of femtotesla per root hertz, for example. And so a typical value of these ZULF-NMR spectrometers is maybe between 10 to 50 femtotesla per root hertz, whereas sort of the theoretical minimum is, of course, quite a bit lower than that, below 1 femtotesla per root hertz. But unfortunately, in these experimental setups, there's always other noise sources that are hard to fight.
Thomas, there is one question from Dima. In equation 2, the longer you measure, the worse sensitivity.
Well, I think I kind of just addressed that issue, right? That the that it is independent of the measurement time because your SNR, of course, improves with the acquisition time, so it's independent. And I'm happy to discuss this with Dima later. Okay, very good. Okay, so now let's kind of think a little bit more about the various details of these setups. So let's talk about prepolarization and sample shuttling. So here's another image of a typical experimental setup, and I want to just say a few words about maybe a good implementation of how to make a sample shuttle. And definitely my favorite by far, even though you can also probably use stepper motors or et cetera. One of the easiest ways of implementing this is just by actually building a small little pneumatic setup, something that just sucks the sample up and down or pushes it up and down. And so here's sort of a schematic of how we've implemented that. So we just have a solid state relay that we control with a TTL that turns on a voltage or turns it off, and that's plugged onto a solenoid actuated valve where we can turn on or off the vacuum. And so it's simple enough. You turn the valve open, it connects it to the house vacuum, bloop, your sample goes up, it gets prepolarized, you can leave it there for the desired amount of time, and then you turn the vacuum off. And then if you set it up in a way where you can also have maybe some house air that presses the sample back down as soon as the vacuum is off, then it goes bloop, back down, and it's really kind of easy to assemble. So it's definitely sort of, if you're kind of asking yourself, oh man, I really want to, shuttle my sample, I think pneumatic sample shuttling is really something rather straightforward to implement. Good. Okay. So now this one way of hyperpolarizing was through prepolarizing in a permanent magnet, and as you know, and as Kirill said, parahydrogen-induced polarization is one of my favorite hyperpolarization techniques to use. And so I want to just share a few sort of technical aspects in terms of implementing parahydrogen-induced hyperpolarization. So obviously the first thing that we would need to do is make parahydrogen. And I think the most important part about the slide is to buy the right catalyst. So that's why I have it here on the bottom of the slide. It's this 30-50 mesh iron oxide. And I've tried other things, such as charcoal, which in principle is also supposed to work. And I've also tried iron oxide with different mesh sizes. But it really has led to a ton of problems and huge delays of the work in the lab. And so now we finally switched again back to the right proper material, and everything is wonderful. And the conversion from orthohydrogen to parahydrogen is fast. So on the right, I show the fraction of parahydrogen you can enrich at a certain temperature. And as you can see, if you go to liquid nitrogen temperature, you can get like around 50% parahydrogen. And then if you have maybe a cryocooler with a cold finger, as depicted here, you can easily go to 30 Kelvin. And 30 Kelvin is good enough to get almost 100% parahydrogen. Closer to 20 Kelvin, I guess. But you can see that you get into this regime close to low temperatures where you can get very close to 100% parahydrogen relatively easily. Okay, so then another way of making the parahydrogen is maybe just with liquid nitrogen setups, and that's particularly easy. So for example, we've designed this little thing that we call the paracube. And here you see a coil in the middle of this setup that just gets submerged in liquid nitrogen, and it's filled with this iron oxide that I was just talking about. And on the surface of these iron oxide particles, the interconversion from normal hydrogen to parahydrogen can take place, and you can enrich the parahydrogen. And so really what this means is that anybody that is interested in implementing parahydrogen, the sort of barrier to get to parahydrogen is very low. And it's really kind of an easy technique. And sometimes I would even say parahydrogen-induced polarization can sometimes be even easier than some kind of prepolarizing pneumatic shuttling setup. So one sort of very important technical aspect about bubbling parahydrogen through your solution is the short valve. And this is kind of what I'm trying to illustrate here. So in the bottom, you see the sample that it gets hyperpolarized by bubbling parahydrogen through it, and then some magnetic waves emanate from there that we want to detect with a zero-field magnetometer. And you see this TTL-controlled short. And we have it normally open. And if this valve is open, what happens is the bubbling is stopped. Let me explain that. So let's say you have a capillary that goes into the bottom of your NMR tube, and then there's some exhaust where the parahydrogen comes out, and at the end there's a needle valve that controls the flow of the hydrogen overall. If the short is open, then of course there's no pressure difference between the top and the bottom of the solution in the NMR tube, because you've just shorted it out. And this is one of the best ways by far to stop the bubbling quickly. If you don't have that short and you just try to like turn off the bubbling just by stopping the flow, it takes forever for the bubbles to stop. And so this short valve really is extremely helpful in terms of just rerouting the hydrogen around the, and therefore not creating any problems with the bubbles.
There is a question from John. How important is settling?
Yes, exactly. It's very important, right? Because what you want is you want these bubbles to stop quickly and the bubbles to settle quickly. And if you don't have this short valve, that's my main point, the settling takes on the order of several seconds, and sometimes there's still little bubbles coming out after minutes, which is extremely annoying. It creates all kinds of problems. Whereas if you put this short valve on, then it usually settles within just a few milliseconds. So in the timing delay here, you see 0.2 seconds for the setting delay. So that's 200 milliseconds, which is plenty if you have a short valve established that can quickly equilibrate the pressure between what you have in the capillary and what you have on top of your solution.
Yep. Great.
Good. Okay, I guess that's sort of my first part. So any other questions?
It seems up to now all the questions are answered.
Okay, wonderful. Good. Okay. So now let's talk about part B, which is the introductory spin physics of ZULF-NMR. So typically what we do is, you prepolarize your sample, you shuttle it down to the ZULF sensor, and then one of the first things you do is apply a pulse. And so the first thing we're going to do is talk a little bit about the pulse. Let me see if I manage to start this video. So imagine you apply a pulse of DC magnetic field and you have a proton and a carbon. Proton has gyromagnetic ratio 4 times roughly that of carbon-13. So what you will imagine is that the proton will rotate faster than the carbon. Let's look at that, if that's kind of how this animation works. Here we go. So, and yes, so not surprisingly, after having said that, the proton turns 4 times faster than the carbon. And so then if you apply, say, 2 rotations to the proton, then you will have applied half a rotation to the carbon, and you will have maximized the difference between IZ and SZ, where I, let's say, refers to the proton and S refers to the carbon. Okay, that's kind of important for the rest of this talk. I refers to the proton, S to the carbon. So we can look at this in a different way, but it represents exactly the same thing. So let's say you have a proton and a carbon that point in the same direction. Let's say they both start at 1. And let's say you would characterize that in a density matrix as IZ plus SZ. So let's say equal polarization on I and an S. And then you apply a pulse. So you turn on DC magnetic field. They both start rotating. I rotates faster because it's the proton. And S rotates slower. And so you see that when S has undergone half a rotation, I will have undergone 2 rotations, and you will have maximized the difference between I and S. That's kind of the action of a pulse. So now the important part, why we do this, is because our magnetometer is primarily sensitive to this difference of IZ minus SZ, whereas IZ plus SZ we can actually not detect. Now, that being said, let me go back just to this slide for 1 second. Even if you don't apply a pulse, and you start in this place where you have less carbon polarization than proton polarization, of course, there is a component of IZ minus SZ in here, right? there is already a difference. You just haven't maximized it yet. So you can actually detect a signal even without applying a pulse. But with this pulse, you maximize your signal that you can get. Good. OK, so now we've applied our pulse. We've maximized our IZ minus SZ. And so the next thing is spin evolution and the thing that we detect. So how does spin evolution look like? You've prepared the state, and now you let this evolve. And this is kind of the funny thing that happens. And this is what we're going to talk about a lot now. We're going to talk about why does this IZ minus SZ sort of start interchanging. And obviously, if this is what happens, this modulates the magnetic field. And we can, and that's what we detect, the magnetic field, obviously, with a zero field NMR spectrometer. And the oscillation frequency here is going to be dictated by the J coupling, because that's the only thing there is. So in the formic acid example, which is one of the most simple examples, you have a proton and a carbon, and they're coupled together with the J coupling, which is mediated through the electrons. And the strength in this particular case of formic acid is on the order of 221 hertz. So the difference between these states, the triplet states, and the bottom, which is the singlet states, is on the order of 221 hertz. And that's the oscillation frequency at which these two magnetization vectors keep exchanging and which fundamentally produce the magnetic field that we detect. So I'm going to kind of look at this problem now in sort of from various angles to really try to foster some understanding of why this happens the way it does. So first, let's look at the Hamiltonian itself. So the Hamiltonian is a scalar product of the spin operator I and S. Another way of expressing this Hamiltonian, or another way of writing I dot S, is that it is the three components, Ix Sx plus Iy Sy plus Iz Sz. One very important thing about the zero field Hamiltonian is that it does not depend on a particular orientation, so it's sort of independent of how you turn the system around. The interaction is not going to be modulated by rotations. And the eigenstates of this Hamiltonian, that's what is depicted in the bottom of the slides. Those are the singlet states and the triplet states. So if you calculate the eigenvalues of this Hamiltonian, what you will find is a singlet state of lower energy and three triplet states of higher energy. And their separation is exactly equal to this J coupling. And we name these eigenstates. We name them singlet state. T minus, T0, and T plus are the triplet states. And we can depict them also in a Zeeman basis if we wanted to. That's on the right of the slide. So T plus is just the state associated with the up state, so both carbon and proton spin pointing up. T0 would be a linear combination of the up-down state and the down-up state, specifically the sum of those two. The singlet state is the difference of the up-down and the up-down and down-up state. And then T minus is just the down-down state, both spins pointing in the same direction down. So now let's kind of revisit this idea why Iz plus Sz does nothing in a zero field environment and is not really detectable immediately, and Iz minus Sz becomes detectable. Okay, so this is what I'm trying to show here. If we now take this operator Iz plus Sz and we depict it sort of with these eigenstates that I just shown you, then what happens is that Iz plus Sz is actually a population difference between the T minus state and the T plus state. And so because it's just a population difference, it means there's no expected evolution. The state Iz plus Sz commutes with the J coupling Hamiltonian. And therefore, the populations just sit, and the only reason they would change are relaxation effects. For IZ minus SZ, which is what we detect, the situation is very different. If we take IZ minus SZ and represent it with the states that we've just kind of talked about, T0 and S0, then what we see is actually that IZ minus SZ is a coherence between T0 and S0 and not a population. Therefore, this is something that will move. It does not commute with the J-coupling Hamiltonian. And we can, hope for detection of that. So let's try to explain that yet in another way. Okay, and one other way is to use sort of the things that we're used to on Bloch-spheres and other representations. And one good way of doing this is using zero quantum operators. So let me introduce you to zero quantum operators. So there's three typical zero quantum operators: zero quantum Z, zero quantum Y, and zero quantum X. And the first thing I want you to do is pay attention to the things in the red boxes. Okay. I hope that you recognize the Pauli spin matrices here. So zero quantum Z looks just like a Z Pauli matrix. Zero quantum Y looks just like a Y Pauli matrix, sigma Y. And zero quantum X looks just like an X Pauli matrix. And so now let's look sort of what's in between. Let's look at the operators and why this is useful. Zero quantum Z, we can immediately recognize, based on our previous discussion, is IZ minus SZ. Okay, and now this is cool. We can represent this IZ minus SZ just like a Pauli matrix, just a Z Pauli matrix. And zero quantum Y is a little more complicated. It's like IYSX. Oh, this is a typo. IYSX minus IXSY. And this zero quantum Y is not detectable, does not have any magnetization associated with it. This IZ minus SZ is detectable, and we see it in the magnetometer. And then finally, zero quantum X is IXSX plus IYSY, and can be represented as an X Pauli matrix. So now the reason why this is useful is because now we can actually represent what's happening at zero magnetic field, sort of with the traditional pictures of a single spin 1/2 in NMR, for example. Okay, so to recap, we have the zero field Hamiltonian, which is the scalar product of I dot S. It can be represented as the sum of these three components. And we can identify zero quantum X here. So zero quantum X is IXSX plus IYSY. Therefore, in this equation, we can just write this as zero quantum X plus IZSZ. The initial density matrix at time point 0, we already talked about, is this difference IZ minus SZ. That's the state that we've created. And that's just 2 times zero quantum Z. Now, this is really cool because now we can just make a picture that we are familiar with that feels more comfortable of a spin rotating around a Hamiltonian. Okay, so our starting point is this zero quantum Z is IZ minus SZ, and this density matrix, the zero quantum Z density matrix, is at a 90-degree angle with the zero field Hamiltonian, namely the zero quantum X component, right? So let's look at this one more time. The zero field Hamiltonian has a zero quantum X component. Therefore, there's a 90-degree angle between zero quantum Z and zero quantum X. And the density matrix is along zero quantum Z. It's a coherence, and it rotates around the zero field Hamiltonian. And things are really easy. It's just representation of a rotation. And so if you do the math, it's now easy to solve. The evolving matrix simply is zero quantum Z cos JT, zero quantum Y sine JT, 2 pi JT, I guess. Sorry. Okay. So now let's compare the two pictures. Let's compare the video that I showed you first with this picture of zero quantum Z starting to rotate. So the beginning, I said, is carbon pointing down, proton pointing up in the video. let's run it one more time. This thing starts rotating, okay? And in the middle, you see there's a point where there's no magnetization, where they both kind of cancel each other out. And that's when our rotating density matrix hits 0 quantum y. 0 quantum y has no magnetization associated with it. It is not detectable in the magnetometer, and therefore the picture of the video on the right makes sense. It keeps rotating, becomes minus 0 quantum z, then becomes minus 0 quantum y, and rotates back to become, again, 0 quantum z, which is iz minus sz. So then this is finally the spectrum that we obtain, and hopefully we have now a little bit more of an understanding why we get one peak exactly at 222 hertz, which is the J coupling here, and it's the energy difference between the triplet and the singlet states. Maybe I'll take a quick break here for questions.
Yes, we can invite, but right now I can't see new questions.
Okay, sounds good. All right. So things get a little bit more interesting once you start increasing your spin systems. For example, if you have methanol that has a CH3 group, that actually shows peaks at 1 times the J coupling and 2 times the J coupling. So at similarly, now if you have ethanol and you add more spins, then you have a CH3 group, again, that shows peaks at 1 times the J coupling and 2 times the J coupling. And you can already tell that there's now some splitting that occurs in addition to these kind of simple rules, which is due to additional J couplings that are much smaller, say between the protons on the CH2 group and the protons on the CH3 group. In the bottom, you have the carbon-13 label at a CH2 group, and that gives you J couplings at 3½ times the J coupling. So experimentally, this is kind of what we're observing. Simple 2-spin systems give you 1 line at the J coupling. CH2 groups with 3 spins give you lines at 3½ times the J coupling, and then CH3 groups give you lines at 1 times the J coupling and 2 times the J coupling. So now the question is, how do we understand that? How can we analyze that? And what you have to do here to really understand this very well is kind of follow the traditional rules of addition of angular momentum. So if you take a spin 1/2 and you add another spin 1/2 to that, then the rules of addition of angular momentum tells us that this splits up into a spin 1 manifold and a spin 0 manifold, which is exactly the singlet and the triplet states that you see above. So the singlet state is the spin 0 manifold, and the triplet states is the spin 1 manifold. Now, if you go ahead, and this is kind of the thing that we analyzed in full detail. If you now go ahead and add yet another spin to this problem, then you get a spin 1/2 manifold, 2 spin 1/2 manifolds, and a spin 3/2 manifold. And the way the energy levels unfold is shown above with the green arrows. And now the separation between the bottommost energy levels and the highest energy levels is 3½ times the J coupling, which is why the observed signals occur at 3½ times the J coupling. Next, if we now, let's say, go to a CH3 group and we add yet another spin 1/2, then you get further spin manifolds, a spin 1 manifold, 2 spin 0 manifolds, 2 spin 1 manifolds, and a spin 2 manifold for the total angular momentum. And here you see energy separations that are given by 1 times the J coupling, as well as energy separations that are given by 2 times the J coupling, which is why those are the locations where these lines appear in the NMR spectrum. The other thing that becomes very important here are the selection rules. So you can see, for example, I didn't draw any arrows between the top spin 1 and the spin 2 manifold, and that's because the selection rules do not allow this transition to be observed if you evaluate the transition dipole moment. There's one funny one, which is delta MF, which is whether you allow transitions from say as an MF minus 1/2 to MF minus 3/2, for example, or if you always go from minus 1/2 to minus 1/2. And this is kind of irrelevant if you're perfectly at zero field, because they're all degenerate. All the MF values are degenerate, and therefore, whether your delta MF value is plus minus 1 or delta MF is 0, it'll still predict the same frequencies. But what's very cool, and which is something we're kind of working out right now, is the fact that you can kind of control the selection rule simply by changing the direction of detection. And I will illustrate some of these examples later.
Thomas, sorry, Khalif asks to explain the selection rule again in the middle case, please.
Yeah, so the way it's kind of shown on this slide is that the energy, you can calculate the energy of all of these levels based on the total angular momentum F, the total angular momentum of the protons, and the angular momentum of the carbon. And the selection rules, once you evaluate it, this is a lot of work to really kind of work them out in detail. But once you do, you find that the delta F selection rule, which means change of allowed change of total angular momentum, is either 0 or 1. The change in angular momentum of the protons that is allowed is 0. And so with these selection rules, you can then start drawing these arrows, and you can then know which manifolds you're allowed to connect and which ones you're not allowed to connect. But the details are not really fully covered on the slide. It's just illustrating the procedure.
Can I also ask, probably in some non-zero field transitions within, let's say, triplets also become allowed and observable, right? So
yes, correct. And those are very low frequency components then in the spectrum. And we'll talk about those a little bit as well. Okay, so let's just, I just want to show you just one more example to like drive home the main message.
I see. There is one more question about this middle, so there is confusion. What is the difference between bottom 1/2 and upper 1/2? If you can comment on that.
Yeah.
In the middle, in case of two protons.
Yeah, I understand the question, and I remember evaluating the Hamiltonian and calculating the energies. If I remember the answer correctly, I believe that what happens is that the total angular momentum F is 1 in both cases, but the combination of K and S is different. So the total angular momentum of F is K plus S, and there are combinations of K and S that can give you the same F, but because K and S are different, therefore they have different energies. So what I'm saying is, in both of these spin half manifolds, the total angular momentum F is obviously the same as 1/2, but K and S are different. I don't 100%, without thinking about it more deeply right now, remember exactly what the combination. I mean, S. Yeah, sorry, I don't 100% remember right now the details of that. Okay.
Yeah, there is discussion in the chat, so I think it's fine. No worries.
Yeah. Some of my slides stopped advancing. Here we go. So one other example that also illustrates this very beautifully, I believe, is that for ethylbenzene, for example, if we hyperpolarize this by PHIP, we can do very nice assignment of the various peaks in the spectrum to the molecule. And I think this is the hallmark of NMR in general, where we can really extract sort of molecular information in an intelligent way from the molecules, and ZULF-NMR can do this, which is just absolutely amazing to me. So the CH3 group, shows peaks at 1 times and 2 times the J coupling. The CH2 group shows the peaks at 3½ times the J coupling, and then the directly bonded single pairs just show the peaks at 1 times the J coupling. And then, of course, you see additional splitting, which is due to the perturbation of the smaller, weaker J couplings. And I think that Michael, after my talk, will in very much detail cover those topics. Good, okay, so then I'm going to stop here and then in a moment sort of move towards the more advanced topics. Okay, good. So in these more advanced topics, what I kind of want to briefly illustrate a little bit more is show some examples of these sort of perturbing fields and possibilities of analyzing them, but only really to give you an impression. As I said, Michael Taylor will give you much more detail. Then I want to talk a little bit more about this idea of what happens if we detect in different directions under a perturbing field. Some really interesting effects that happen to the zero field spectra there. And then finally, I want to go back into the math a little bit of how to analyze the spin physics of PHIP in zero field environments. So first, here is sort of a much more detailed analysis now, for example, for this ethanol labeled at the 1 position with carbon 13. And we have, acquired these very, what you can do is you can kind of really dive very deep into these questions of how to add these additional angular momenta and then do perturbation theory. And then even for these types of more complex systems and the additional splittings, work out all the selection rules, work out all the different kinds of angular momenta that are involved, and then find exactly the energy level diagram for these systems. And you can do that, for the case of carbon-13 labeled ethanol, which obviously very quickly, even though it's a relatively small molecule, becomes kind of complicated for the other one as well. But what I really want to focus on is on a slightly sort of simpler question, which is the delta MF selection rule. And first, I want to point out that this is slightly arbitrary if there is no magnetic field. Because whether you paint the picture, like in the top, where you have transitions between, say, the singlet in the middle and T0, which is kind of how I depicted it when I said we have IZ minus SZ. Or if you depict it like in the bottom, where you have transitions to the other lines, the frequency doesn't change if there's no magnetic field, right? So what is kind of the difference between these two pictures? Really, the only difference is that you say something silly, which is that in the top picture, you say your initial density matrix is IZ minus SZ. The Hamiltonian, again, this is kind of the critical part, is rotationally invariant. So it really, if there's no magnetic field. And then you detect along that same direction, the Z direction. And if you kind of build your math in that way, then your selection rule will be delta MF equals 0 and will give you all the right answers. If you do it differently, if you say, well, maybe my initial state is IX minus SX, again, your Hamiltonian is rotational, and you detect along X, then your selection rule is delta MF equals plus minus 1, and you will still get all the right answers. And it kind of really doesn't matter. It's just an arbitrary choice that you make. But obviously, it changes the picture quite dramatically in terms of what you're thinking you're doing. This becomes extremely relevant, however, when you start applying a magnetic field. So let's kind of look at this problem. So for example, as kind of first done together with Ledbetter, if magnetic field that is 90 degrees away from the direction of detection, then what we actually have is this delta MF equals plus minus 1 selection rule. And therefore, at no magnetic field in the formic acid, we detect just one line. And then if we apply a magnetic field, and we have this selection rule, the delta MF equals plus minus 1, then we detect two lines in the presence of this magnetic field. Similarly, this can also be shown, for example, for a more complicated system such as acetonitrile. If there's no magnetic field, you see two peaks, 1 times the J coupling, 2 times the J coupling. And now we apply this magnetic field 90 degrees out of the direction of detection. And the selection rule is delta MF equals plus minus 1. You see all these lines going to the sides, and you get all kinds of interesting splitting. And this is very useful in the sense that these multiple structures really reveal much more molecular details. So for example, you can learn exactly what kind of groups you're dealing with. You can also learn what kind of gyromagnetic ratio you have involved, if it's a carbon or a nitrogen, if you need to make that differentiation, et cetera, et cetera.
Thomas, here's an interesting question from Ilya.
Yes.
Is quadrature detection possible here? Simulations seem to show that some frequencies here are positive and others are negative and reflected back. Yeah,
this is this is correct. And Ilya and us have been working together very closely. And what I'm going to show next is actually the simulations as a result of working together with Ilya, where we show that now the spinach packets reflects exactly how this is done without quadrature detection. So that means we cannot differentiate between negative and positive frequencies. But if there was a way of how to implement quadrature detection and to differentiate between negative and positive frequencies, then we could certainly sort of maybe gain even more information. So bear with me, and I'm going to show those slides in just a moment. So this is exactly.
I'm sorry. There is also probably a connected question. What is the origin of peaks at the very left part? So I think zero frequency, right?
Yeah. So here I can comment on that here. So there's two peaks here on the left part, for example, in the case of formic acid. One of the peaks is a transition that happens between these lines. So between the split lines because of the magnetic field, and the other one is actually simply protons oscillating around the magnetic field. So imagine you didn't have any J coupling, you only had water, for example, right? Like some kind of sample that had no J coupling, then you would still see this this peak, which is simply the magnetization oscillating around the magnetic field, this weak magnetic field that you're applying, which has very low frequency in this case. So again, one of them comes from the actual spin system and depends on the magnetic field that you applied onto the spin system and the level splitting that you've obtained, and the other one is sort of much more trivial. The other peak simply magnetized protons oscillating about the magnetic field. The most type of the Mark spectrum.
And the frequency is different because the triplet, the coherence within triplet is multiplied by square root of 2 or something. Why?
So if you look at this molecule, the picture concerns itself primarily only with the carbon-13 and the proton. But for example, there's also an exchangeable proton on this molecule that we haven't even talked about, right? And this exchangeable proton is not coupled to anything. And that's really what we see. So it's really outside of this picture that we've drawn out here.
And I also noticed a question from Raman. Is it absolute spectra or Ryu, absolute value or Ryu part?
These are real spectra.
Yeah.
We'll talk a little bit about imaginary versus real versus absolute a little bit later, but these are all real. You can tell that it's real, for example, because you also have negative contributions here in some peaks of the noise.
Yes.
Yeah.
Yeah, thank you.
Okay, so let's come back to this question of how can we control this delta MF selection rule. So for example, we've now just simulated with the help of Ilya, as indicated by his question, And these two cases, one where the magnetic field is applied 90 degrees away from the direction of detection, and another case where the magnetic field is applied exactly along the detection of direction. So on the left, the way this is done is that our initial state is Ix minus Sx, our field is along Z, and then detection happens along X. And this is basically where the field and the detection are not in the same direction. On the right, what we simulated is we have an initial state that is Iz minus Sz. We apply a field along Z, and then we detect along Z. So everything is in the same direction. In that case, your selection rule is delta MF equals 0. And even though you have a magnetic field on, you only see one single line. So in this case, it's particularly simple, quite straightforward. But only simply by going to a CH3 group, things already become much more messy. So, for example, here in the acetonitrile with this CH3 group, if you have a magnetic field applied 90 degrees away from the direction of detection, you get interesting multiplets, such as a doublet at 1 times the J coupling and a 2 times the J coupling. You get another structure. Whereas if you now apply the magnetic field along the axis of detection, you can see that the line at 1 times the J coupling does not get split, whereas the higher multiplet, even though everything is along Z, still experiences some form of splitting. So kind of modulating the selection rule, which I think is rather intriguing. Okay, so I'll stop here and take some questions.
No new questions.
Okay, great. Okay, so then let's go into the spin physics of how to describe parahydrogen-induced polarization at zero field. And this, will help us understand, for example, the antiphase pattern that we observe in these PHIP polarized spectra. So in order to understand this in a little bit more detail, let's first of all look at sort of the chemistry of how we do this. So one possible way of introducing parahydrogen into molecules is through hydrogenation. We take parahydrogen in its anti-aligned singlet state. It plops onto, for example, styrene in this case to form ethylbenzene. And then what actually happens is that because you're at zero magnetic field, you can not really form magnetization, but instead what you get is sort of singlets spreading everywhere. So let's kind of put that into a little bit more mathematical terms. So you start out in a singlet, so something like I1.I2 on the parahydrogen, and you plop it, for example, let's say into this 3-spin system that is shown in the bottom. So in this case, there's only 3 spins. You've just added 1 carbon-13, for example, which is in light green. And notice the colors here. Pay some attention, please, where you can see, okay, the blue is the singlet state that we start out with. The green is a singlet state between 1 proton and the carbon-13, and the red is the singlet state between the directly attached proton and the carbon-13. And if you look at these simulations and you look at what happens at these various possible singlet orders between these 3 spins as a function of time. So of course at time point 0, you're in a situation where the only thing that you have is singlet order between the 2 original spins that were just put into this molecule. So that's why blue is all the way at -1. Everything else is at 0 in the beginning. So red and green are at 0 in the beginning. Then you let the system evolve, and you see what you obtain are singlets in all possible other combinations. And if you do the same simulation for ethylbenzene, then exactly the same thing happens. You put the singlet state onto 2 specific nuclei, and then you let the system evolve, and what you obtain are singlet pairs, or ij.ik between all possible spin pairs you can imagine. So what the end result is that the generated Hamiltonian, the generated density matrix aligns with the J-coupling Hamiltonian. So notice that the symmetry of the Hamiltonian and of the density matrix that get formed is very similar. They're both these kinds of scalar orders. Another way of doing parahydrogen-induced polarization is through the Saber technique. And here, fundamentally, in terms of spin physics, what's going on is rather similar in the zero field environment. So the substrate, for example, pyridine, can attach to these iridium compounds, and there's a reversible exchange, so it pops on and off. But while you are bound to this iridium complex, the singlet that is on the hydrides, on the two hydrogens, also propagates through the system and forms more singlets everywhere else inside of this molecule. And again, just to say the same thing one more time, the generated density matrix aligns itself with the Hamiltonian, which is just a J-coupling, and they are all represented by the same operators. They're all represented by just scalar products of the spin operators. So now we can go back and try to understand the experiment again in the zero quantum environment and that we introduced earlier. So as a quick reminder, there's zero quantum x, which is ix sx plus iy sy, so rather similar to the Hamiltonian. There's the zero quantum y term that sometimes we have evolution through, but is not observable. And then there's zero quantum z, which is really where the magnetization is, which is iz minus sz, and that's what we observe. And again, the important part is that they behave just like Pauli matrices, so you can represent this as simple rotations, and you can kind of learn something here. So let's look at picture one all the way on the left. Here, this is where we start. So the zero field Hamiltonian, right, is represented by ij, ik scalar spin products. And we've just discussed on the previous slides that the density matrix in the beginning is also exactly in that same direction. The density matrix in the beginning basically relaxes into the zero field Hamiltonian direction. And so now we need to read out a signal. So again, the typical procedure is we apply a pulse and then we let this thing evolve, and we shall see what we get. So the pulse now acts a little differently. So before we had zero quantum z, we started at iz minus sz and then converted it into we wanted to maximize that with a pulse. Here what we're doing is a little different. We're applying a pulse to rotate zero quantum x into zero quantum y. How do we do this? We apply a pulse, and what that means is we're generating an interaction that acts in the z direction, right? A pulse is typically of magnetic field is in the z direction because that's our quantization axis. So during the action of the pulse, the Hamiltonian goes from zero quantum x onto zero quantum y. That's what is going to give us most signal. Once we've prepared this thing at zero quantum y and we turn the pulse off, then the Hamiltonian that is active, that's all the way on the right, is now along zero quantum x again, because it belongs to the J-coupling Hamiltonian. And now the density matrix that is along zero quantum y will start rotating just before when we discussed this, and generating eventually zero quantum z, which is the detectable thing that we observe, the magnetization, the magnetic field that we detect. So just to basically bring this back together again, right? So if we start with iz minus sz, that means we would start along zero quantum z, and then we see the rotation. Now in the case of parahydrogen, it's a little different. We generate zero quantum y with a pulse, and then it rotates to produce detectable zero quantum z order. And
Thomas, can I just
yes.
Yeah, we have 10 more minutes. Can you? Is it fine for you?
Yes, of course. So, okay, I mean, I guess we're essentially done with part 3. And so the last part, so I guess I'll take some questions. The last part is not going to take too long, if there are questions about sort of these spin physics aspects. Okay, that's fine.
There was a question about I1, I2 singlet. Should not singlet be equal superposition with a minus? Probably, yeah. You can comment it. There, it's probably the question was
maybe there's a
addressed to certain slide. Yeah.
Oh, that is minus I1
yeah,
I2, not plus. Sure.
Yeah, it should be minus, I think. Yeah.
Yeah, no, of course. Usually, you know, the way it gets represented as something like a quarter identity minus I1 dot I2. But you know, all you're doing is multiplying on, which doesn't fundamentally affect the results of your simulations.
There is one more question, Thomas. Why are rubidium spins aligned by a circularly polarized laser beam?
It has to do basically with the angular momentum associated with that you have in circularly polarized light versus non. So a circularly polarized light has an angular momentum that can be imparted on the spins, which then makes them align. If you have say linearly polarized light that has equal amounts of +1 and equal amounts of right and left circularly polarized light, then this angular momentum cannot really be put onto these rubidium vapor spins.
Yeah, he also asking through spin orbit coupling.
Oh, I see. Yeah, I'm kind of the wrong person to discuss those questions.
I think tomorrow
really know the answer.
Tomorrow will be a whole talk about this aspect of magnetometry.
Yeah.
So,
I don't know the details of those questions. I'm sorry.
No problems. Yeah.
Okay, good. Okay, all right, 10 minutes. So that gives me just a brief moment to give a shout out to sort of our recent explorations with Saber and PHIP. So these are sort of NV detected Saber and also some Razer effects and the route to chaos that we observe. So let me just give a very brief sort of overview of the Saber enhanced NV spectroscopy experiments that Nitya did in the lab of Ron Walsworth. And so we traveled there a couple of times, helped them set up the Parahydrogen system, et cetera, and got all the Parahydrogen business working. And essentially, the way this works is we just bubble Parahydrogen through a solution that contains the Saber system, and then in that cuvette in which the bubbling happens, there's also an NV diamond embedded in that cuvette. And as a result, you get very strong polarization of pyridine, for example, very close to the surface of these NV centers. And so then with the NV-NMR spectroscopy techniques, you can detect these signals. And so, for example, here, these are some of the central results, is that we have a single shot measurement of 100 millimolar pyridine, which is quite low compared to anything else that has been detected with these NV centers before. We have 10 to the 5 signal enhancement over the thermal polarization at those fields, and the sort of sensitivity measured in femtomoles per root hertz is as low as 13. Which I think is also a sort of a new milestone in this technique. So I think in general, right, like all these techniques, be it NV-NMR, be it ZULF-NMR, be it any other kind of way of detecting NMR, will profit greatly from these types of hyperpolarization techniques. Another sort of central result is that we can detect even as low as 1 millimolar pyridine with an SNR of 50, for example, after 5 minutes of averaging, which, and what we did here is just go down with the concentration. Of course, pyridine is sort of the most typical molecule that we do this with. We can also do this.
Sorry, Thomas, there is a question from John about previous slide, I think. That NV detection picture assumes the sensing volume associated with single NV stochastic polarization detection. How big was the actual sample in the experiments? Okay.
Yeah, the actual sample was large. It was 0.5 milliliter. So the assumption has to be made, right, that we're only detecting spins from very close to the NV center. Yeah, but you can also, detect biomolecules with these NV centers. For example, we detected vitamin B3, and so maybe this is a step towards monitoring sort of the biochemistry in very small volumes on the surface of these NV centers. So the next kind of topic that I wanted to kind of briefly show that I've been fascinated with is sort of all kinds of chaotic behavior that can emerge in NMR. So here's one of the central results of what happens when you have very, very high polarization inside of an electronic circuit that is highly resonant. And you see this FID. And in the beginning, in panel 1, you detect frequencies from 2 spins, HA and HB, that have different chemical shift. And then you have things that are, usually associated with the topics of chaos and intermittence. For example, that the detected spins change sort of randomly, kind of, between being the one spin and then the other. And you can even see that in the FID. So for example, when you look in B, you can see how the frequency starts out kind of regularly, then from a sudden becomes faster, then goes slower again, and then becomes faster again. So it's kind of interesting to enter this world of chaos and intermittence theory. And we're now kind of taking this apart bit by bit in terms of a theoretical level. And it's really kind of astonishing that the theories that exist can actually kind of describe this behavior, and we can start actually to understand these types of messes to some extent. So let me just say a few little words about RASER in general. So we have some pumping that is just basically provided by the parahydrogen. So the parahydrogen produces more and more polarization, and it's important that it produce negative polarization because you need a population inversion. And the cavity, instead of being mirrors like in a laser, is established by a highly resonant circuit, ideally with a large Q. And so then as a result, the RASER provides sort of a continuous source of a spontaneously emitted NMR signal. And basically what that means is you can acquire your NMR signals for a very, very long time. And in this particular contribution, we did 2 types of experiments that we describe. One is Saber with pyrazine, and this was chosen with a purpose. So pyrazine, if you look at the structure above, only is associated with one single line, one single frequency, because there's no chemical shifts present. And it gives us sort of a very nice model system to study RASER effects. And then much more complicated is shown on the bottom, where we implemented parahydrogen-induced polarization through hydrogenation, regular PHIP, and then observed these types of RASER effects just in a commercial 1.4 Tesla Magritech device. And the molecules that we have polarized were ethyl acetate, and then in the bottom, hydroxyethyl propionate. Which established much more complicated sort of spin systems. And if you look in the bottom, there's HA and HB and ethyl acetate and the molecule in the bottom. And those have different chemical shift, and those are the kind of weird signals I've been showing you in the beginning. One of the most important things about the RASER is that you need to cross a polarization threshold. And this is the equation here for the polarization threshold that is shown on the left. So if your polarization so your polarization is high enough to have RASER effects once it kind of exceeds the values here. So you can see that a large Q of the coil is useful, a large number density NS is useful, And large T2s are useful in order to have lower requirements on the polarization. And so, but what we explore in this system here is sort of what happens when you go way above this threshold, and all kinds of interesting things appear. So in these kind of simulations, what we show is that at very, very high polarization levels, that's kind of A and E, you can get these kind of frequency comb effects. And then as the polarization goes down, as you're kind of a little bit lower in polarization, you can get into this regime where you can get crazy chaotic air. All kinds of frequency coming from a system from a sudden. Then when your polarization drops even more, you can get again back into some regime where you get frequency combs, and they change, and the distance between the lines changes because of frequency pooling effects in these razors. And so what is presented in this paper is that depending on the line splitting, for example, or essentially the J coupling in these molecules, this behavior is kind of predictable. Like you can exactly calculate and predict how much these line splittings in these frequency combs or in the single spectra are going to be, and also at what point of the polarization or the equilibrium population inversion, which is shown in the bottom of the graph, you get into these chaotic regimes. And things kind of unfold in interesting ways. And one of the sort of take-home messages that I thought was really interesting is that a simple model, simply using two coupled lines, also already kind of predicts the behavior of these systems that are much more complicated in nature as a function of polarization. So you can imagine that when you start with a very, very large polarization, and then you acquire the FID, that the polarization decays slowly along that time. So then we basically can observe what happens with a razor as a function of decreasing polarization. And so we've taken different bits of the FID and Fourier transformed them individually. And the same thing we do with a simulated FID. That is only a simulation of two coupled lines. And you can see that in the very, very beginning, at very high polarization levels, the behavior is broad and very chaotic, and then kind of decays into sort of more orderly behavior until at the end, there's only enough polarization to be over the threshold for one of the lines. That's kind of all the way in the bottom in 5. And you can only observe that line for a very long time. So yeah, and I guess with that, I'm going to conclude that Parahydrogen and ZULF-NMR are beautiful, and I'm happy to take any questions.